So this video, we're going to revisit a series of videos that I did before. I'll put a link down below. I designed this little test board for using on a vector network analyzer. And it includes several options of putting parts on the board so you can do component testing. The one that I'm interested in mostly is the third one over, left to right. And it is basically a 50 ohm transmission line with a 100 picofarad capacitor in series. And then the VNA would connect on the top, and there's a 50 ohm load on the bottom. So basically you have a transmission line, capacitor, transmission line, 50 ohm load, all right? So it's like a capacitor and resistor in series. That's the circuit that we're going to be taking a look at. And this is the result that I got initially. When the frequency is low, then the device looks like an open, and you'll have the Smith chart over on the far right-hand side. As you increase the frequency, you'll follow the line of constant 50 ohms. The real part is going to stay at 50 ohms, and the reactance will change, and we'll follow that curve. And we'll follow that curve all the way over. Ideally, we would follow that all the way over to the very, very center of the Smith chart, where we're still at 50 ohms, but our reactance goes to 0. So, and that's the J component, right? Capacitors are negative J, and then when J equals 0, we'll be back to the position in the center, which is a perfect 50 ohm load. Now, the interesting part of this experiment was that we got this little kink. This little kink started around 400 megahertz, 500 megahertz, and it bent to the left. And so a lot of people surmised what might be causing this. And one of my viewers was gracious enough to do a model of this device, and a friend of mine was able to do some other measurements on this device. So let's take a look at those things. All right, the first thing we're going to do is how good are my transmission lines, all right? So if we take a look at the second one over from the left, it's just a straight through transmission line, right? So if it looks like 50 ohms, great, everything's going to be hunky-dory and we'll just be fine. We can measure the S11 parameter and see that it should be at 50 ohms all the time. Everything's fine. Or we could do a through measurement. So what my friend did was to, he actually bought 100 of these boards because he's going to be able to use them at work. But he did an S21 measurement. So he connected two connectors, and he's going to measure through that little transmission line and see how well it does at different frequencies. So here's his data. Now, he had access to a Keysight VNA that goes up to 50 gigahertz. So obviously, this transmission line does not go to 50 gigahertz, but you can see that it's really good to 5 gigahertz. He said that it's only down about 0.85 dB at 5 gigahertz. And so we can say this transmission line is operating very, very well up to 5 gigahertz. Now, all of my measurements only went to 1.3 gigahertz. So basically, the idea that the transmission line is bad, that's been proven that the transmission line is good. How do we make the transmission line even better? If we wanted to go to higher frequencies, we could use more expensive connectors. We could use a better dielectric board. Maybe we can put in more via stitching. We could do a lot of things to try to increase this. But for my use, hey, this thing's perfect. It way exceeded my expectations. So looks good to me. All right. So the other viewer looked at doing a model of it. And so here's his model. It's going to be a 100 ohm resistor in the center, which he measured his board at 93.7 picofarads. He measured some ESR, some resistance of the capacitor, and it's measuring maybe 4 ohms, something like that. He thinks maybe that's a little bit on the high side, but for this model, we can say it's about 4 ohms of series resistance. And it also has inductance, right? Capacitors aren't perfect devices. They have resistance and they have inductance. And so he did some measurements, and his measurements said that the inductance was about 0.76 nanohenries. All right, and then there's a little transmission line I set on either end, and he also was going to measure the parameters of this thing. All right, so here's the output of his model. And this is what his curve looks like. It's got that funny little kink to the left there and a little loop-de-doo in it, and happening around 500 megahertz. Just for reference, here's my measurement, and here's his again. So yeah, they're pretty spot on. So that's very encouraging. So I had an idea for an experiment. There's some questions about the calibration of this setup. So this is the Cal standard that I was using. It's homemade, open short load, and the open is easy. The short is just blobbing that with solder, just creating a plane of short. And then the load was 2 100 ohm resistors, so you got a nice 50 ohm load. So that's how that thing was built. And then you have a predictable plane of calibration. The plane of calibration is on the surface there where the open and the short and the loads are. So everything is on the same plane. Now, if you take a look at the board, though, we're calibrating at one plane, which is on that connector in the upper section. So the plane of calibration is not where the device is. There's some electrical length to get to that 100 picofarad capacitor. So you can do what's called a port extension. You can tell your VNA, even though I've calibrated at one location, I'm going to set some length as a port extension, and mathematically the VNA will act like it was calibrated at a different location. And so I'm going to try that out, see if we get any different results. And then the other thing I thought of doing is trying to create a calibration standard exactly where the part is. So this was my attempt at making a calibration standard, a short, an open, and a load, so that those three things happen at the physical location of where the device is going to be. So the short is just a short. That's pretty self-explanatory. The open is just the capacitor is not loaded. And then the load, again, is 2 100 ohm resistors. So let's go out in the garage and try out the port extension and try out the calibration with the new Cal standard and see what kind of results we get. Okay, so let's first calibrate with my self-made open short load. So let's set this thing up. Let's see, measurement. We're going to be doing a reflection measurement. Let's change the display to big. There we go. We have a Smith chart. And we will do, I'm going to turn averaging on to make it more accurate. So I'm going to have an average of 4. Entire sweep range up to 1.3 gigahertz. I'm going to change the number of points to 1601, so we'll have really fine resolution. We'll do a calibrate. We'll do port extensions are off. CalCet is type N. And we'll do a 1-point calibration. It's asking for an open. Somebody reminded me never spin on a connector, and that's a very good advice. So use a wrench. And it takes 4 measurements. Asking for a short. All right, and a load. Okay, so we have a nice measurement of the load. Let's put in the short. The short should appear over on the right-hand edge. And you can see that it's very nice on the right-hand edge. So that's our short. All right, so let's take a look at my self-made calibration standard, okay? And I'm going to put in that short. All right. So this short, we're showing a very big line over on the left-hand edge. It's not a point where the short's supposed to be. And that's because we've calibrated at one plane, but we're measuring at a different plane, and we're seeing the inductance of that trace as a line. We're getting, it's not inductance, it's electrical length. It's rotating in the clockwise direction. So we can turn on port extension, and we're going to put in reflection port extension, and then we will add some length, and I went too far, and so right about there, oops, right about there, about 68 picoseconds, we now have the port extended to the electrical length where all of our devices are going to be. Okay, so now we have a good port extension, and yes, I know that opens funny, but that's just the way it is. Now we're going to put on our device under test. And let's see how we do here. And it looks about the same. It hasn't really changed very much. So if we can remember what this one looks like, it looks like it goes to, let's zoom in a little bit here. Looks like it goes to about minus J10, value of 10 in the minus J direction until it bends over. If I turned off the port extension, then it would look like that. So the difference between having an extension and not is between these two things. So it's bending over at about the same place, but it's a smaller excursion. It's more along the lines of an inductor. If you know the equal lines of reactance for an inductor, it's kind of following that curve. It does have the little loop-de-doos and everything, but anyway, our port extension is there. But yeah, we're getting about the same. We're getting about the same picture. All right, so let's do the experiment now with calibrating with my fancy cal standard, okay? So let's do that. Let's go back. Let's turn off the port extension, and let's calibrate again. We'll do a one-port calibration. Okay, so this is our cal standard. So we will put in, it's asking for an open, so we will attach the open. It's asking for the short. I don't think I have a, I think I lost my averaging. Let's turn averaging back on. Averaging on. There we go. Averaging on. Average factor of 4. I just want to make this apples and apples. There we go. Have averaging of 4 on. Calibration. Everything looks good. We'll do our one port. Hook up our open. There we go. Short. and load. All right, we have a little tiny little dot there right at 50. Very nice. Wow, very good cal. That's when you turn averaging on, it gives you really, really nice numbers. Okay, so let's go ahead and measure our device. And it's gotten a little bit better. A little bit better. So there you go. Let's turn that marker on. I mean the scale in. Yeah. Now we're getting up to almost J of 7. Instead of a J of 10, we're up to about a J of 7. So yeah, it's gotten a little bit better. Let's check the short calibration, make sure our calibration is correct. Just like to double check things. So there's a few things that are very, very easy. That's a load. There are some things that are very, very easy to check when you do calibration. You can make sure your load is looking good, your short is looking good. Yeah, there we go. See, we have a very nice calibration. Our short is exactly where we want it to be. And let's put back in our device under test. Yeah, I'm quite pleased with this. So it does seem to be a little bit better than port extension. So I take it back. Yeah, we're looking quite good. Now people say, well, why is it not following the 50 ohm line? And that is the loss in the system as the transmission line loses energy. Instead of following the 50 ohm line all the way around, you'll slump off of it and go to the 49 or 50, maybe a 51. Let's see here. Let's zoom way in. Yeah, about 52 ohms. So anyway, there you go. I am still learning lots about the RF world. There's lots and lots to learn, and this has been a great experiment. So the boards have come in real handy to run these little experiments and stuff like that. I think my friend was going to use these boards to try to measure some ferrite beads, which I'm very curious about. I'd done a video on that before, but on big devices, not on little bitty surface mount devices. So I don't have any of those in stock. But yeah, there you go. Hope it was of interest and answered some of the questions maybe you had from the other videos that I did. But yeah, there you go. Oh, I've got an update for you. My friend just texted me. He was using the wrong SMA connector on the boards, and he had a wide base for his SMA connectors, and he went to the narrow base, which my board is laid out for. And so my boards went from a 5 gigahertz board to a 9 gigahertz board, which is good news. Here is the new S21 plot, seeing that, yeah, it's much, much better. Very, very nice. Thank you. He works on very fast fiber optic stuff, and he did a couple other measurements. He sent some data through it. I know some people are interested in eye diagrams, so here's some real eye diagrams. So this one is a 10 gigabaud eye diagram. So yeah, 10 gigabaud. And he also said acceptable was the 25 gigabaud data through the transmission line. So yeah, 25 gigabaud. That's pretty fast.